All right, so welcome back. Welcome back to the channel. So, in the last video, we have covered the part one of word embeddings, in which we have learned about word-to-vec model and also the basic idea of word embeddings and how they function, and also also the advantage of using word-to-vec rather than the normal word embeddings. Right. So, we will. So, as I have already promised in the last video, we will cover glove in this video. The paper called Global Vector global embeddings for vector representation or global vector for uh, representation. I'll just open this paper, so we can just go through. I think you can just go to internet and just search for glove paper, global vectors for word representation. Uh, so we'll just open the paper. So this is the paper. The paper I think was published by Stanford, the smart people at Stanford. So we will be covering the paper in detail, but and also the changes that have been taken. And I haven't covered this before yet, so we'll just cover the main parts of what this covers. So first, I'll just give you a review of what embeddings actually are. Even if you haven't watched the last video, I'll just try to provide you a basic context on what we are talking about. So, of course, when you are building language models, right? Let's say you are building large language models or any type of language models, and you are training language models, you have to find a way, right, to represent each word. So, language modeling refers to building models, building artificial intelligence models, building models that are able to find patterns inside text data. And to build these models, we should first find a way to encode this text, just to encode this text in such a manner that this text is not only is not only this text is not only able to model. So not only these models able to model this text, but also these the representation that we have to give to this text should carry some information about the word, right? So computers cannot understand words, right? Computers only understand uh, numbers, right? Even if you type any number, or even if you type any text in your computer, every word is taken in as a number, as a token, right? As a random number, or each word would be assigned a number, or each letter would be assigned a number. But in language modeling, we should make sure that these numbers have some patterns in them, so that the model can find these patterns and try to build intelligent models that are able to understand language, right? For example, let's say we have a bunch of words, right? Let's say we have let's say we give a two-dimensional token for each word. Let's say we assign two numbers for each word, two numbers, because we could visualize a 2D plane. Let's say we assign a two-dimensional vector, or two words or two numbers for each word, or even n numbers for that. So let's say we are assign two numbers for each word randomly, right? Then we have, if we plot these numbers, for each word. So this cat represents the location of this cat is represented, or is represented by the two numbers. So we'll just plot it in XY graph. So let's say we plot it. Let's say we have two numbers, because we could easily visualize two dimensions. So then let's say we have different words. Let's say laptop here. Let's say a bicycle here. Let's say we have dog here. Let's say we have apple here. Something banana, king, right? Maybe queen here, something. So these are random, right? These words are grouped randomly because the numbers we have assigned to them are completely random. So therefore, as these words do not have a meaning, as these words do not as these words do not store any relations between the corresponding words, it will be hard for language models to model this data. The models cannot model this data, because it is hard for the model to find patterns and try to able to create patterns and predict the next word and understand language and all that. So therefore, using word embeddings, we would be able to change these representations. So each word is given a representation, right, of embedding, which has two numbers in this case, just to visualize two dimensional, or let's say n. So this is let's say let's in a hypothesis word, let's say this is an n-dimensional representation. Maybe we are some aliens or something. Maybe let's say this we could be able to like let's say visualize n dimensions. So we'll be having an n-dimensional vector for each word as a representation. So we use or using embeddings. So we should be able to optimize these vectors or embeddings for each word such that related words are closer to each other. Right. For example, king and queen, they are pretty much related. So therefore, these words queen and king should be closer in the n-dimensional visualization space. So therefore, these should have similar vectors. Queen and king should have similar vectors, and cat and dog should have similar vectors, and banana and let's say apple should have similar vectors, and laptop and maybe bicycle should have similar vectors. So these relations should be carried out or should be tracked by this embedding. So therefore, that is the idea of embeddings. So the main idea, the main thing that we following embeddings is we do optimization, right? We follow the neural network. We'll build a neural network, right, in which we optimize, in which the weights are essentially the embeddings. So we'll update this weight such that related words are closer to each other, and I have already covered that in the last video. So if you are interested, check that out. So in this video again, we are going to cover glove, like global vectors for global, I think, representation for global vectors for word representation. So I'll just read the abstract and you just move on with some ideas. I think we'll just skip some related work and we'll just move on. So we'll just read the abstract first. So recent methods for learning vector space. I think this paper was published at I'll just see. 2014, yeah, pretty old paper. I think Word to Vec was published like 2013 or something. Yeah, in just a year gap, they have this paper has come out. So I'll just read it. So recent methods for learning vector space representations of word have succeeded in capturing fine-grained semantic and syntactic regularities using vector arithmetic, but the origin of these regularities has remained opaque. We analyze and make explicit the model properties needed for such regularizations to emerge in a word vectors. This result in a new global log bilinear regression model that combines the advantages of the two major model families in literature: global matrix factorization and local context window methods. Our model efficiently leverages statistical information by training only on non-zero elements in a word. Okay, we'll just skip that. The model produces vector space. Fine. Okay. Yeah. So, for example, the analogy king is to queen as man is to woman should be encoded in the vector space by vector equation. King minus queen equals man minus woman. Yeah. So it's something that makes sense. Probably not very mathematical, but yeah, I mean, these relations like this should be captured. King minus queen equals man minus woman. Yeah, the relations should be carried out, right? This evaluation scheme favors models that produce a dimensions of meaning, dimension of meaning, thereby capturing multi-clustering data of distributed representation. The two main model families for learning what vectors are: global metrics for factorization methods such as the latent semantic analysis. Number two, local context window models such as skip-gram model for my call up. I think this, yeah. So we have used skip-gram model, I think, in Word to Vec. So I think we'll just carry on. We'll just carry on with the actual thing that I have proposed. I think we'll read this thing, this little paragraph, and see what it has to tell us. Some words might be very mathematical, but if it's very mathematical, we might just leave it. But also, I'll try to cover everything. So the statics of word occurrences in a corpus is the primary source of information available to all unsupervised methods for learning word representations. And although many such methods now exist, the question still remains as to how meaning is generated from these statistics and how the resulting word vector might represent that meaning. So the only information that we have, right? So this is unsupervised data, right? We don't have any labels. We don't have any, even if you learn about linear regression or something, or even binary classification for that case, we would have some data and we'd have an output, right? But here, the only understanding we have is the we only have the access to statistics of word occurrences, right? For example, the amount of word occurring in context of other words. That is the only data that we have, and we should use this data in order to create some meaning, right? We should use this insight to create some meaning. Right? We use our insights to construct a new model for word representation, which we call GLOVE for global vectors, because the global corpus statistics are captured directly by the model. First, we establish some notation. Let the matrix of word co-occurrence counts be denoted by X. Right? We have like, I think, a table, right? So we'll have, I'll just draw the table for you just to make it very, very clear, and even clear for me. Right? We know it's very good to write notation just to make sure, when you get with these variables, we could just use it. So we'll have a table in which, let's say I have, let's say I have a corpus. Corpus is nothing but all the words that the model know, or all the text that the model have access to. And let's say we have 3 sentences. Let's say something like I mm, I like, something, yeah, something maybe pretty simple. So I like chocolates, something, and maybe my name is Joel. And then something like maybe AI is evolving. I mean, something like that, something random text. So what we'll be doing is we'll be just drawing a table. Right? We'll be drawing table. So we'll have a vocabulary. Vocabulary is nothing but all the new words that the model know, or all the words that the model know. Right? We'll have vocabulary. Vocabulary is nothing but all the words that the model knows, or all the words that are present in the corpus. So each word in the corpus will be in the vocabulary. Right? Every word in the corpus will be in the vocabulary. So we'll just group all these words. So let's say I like chocolates, and all these words, my name, everything, and the last word maybe evolving. I'll draw that. So we'll have all these words grouped in this manner, and also we'll have the same words grouped in this manner also. I like chocolate, my name is, and all that. So let's group like this in the table, and we would just get like the co-occurrence of 2 words. For example, we'll just skip that. So we'll just say I and like. How many times does this occur? 1 time. I and like, and I like I and chocolate, maybe 1 time. I don't think we should specify chocolate, maybe, or maybe we'll just give a small value or something. So like this, we group all this data. We'll just give a numbers based on how many times 2 words occur. I think maybe this also should be 1. By the way, anyway, so we would like have a table, right, in which we'll just give a value for like how many times each word co-occurs with any other word. And then by doing this, we'll get a vector, or sorry, a table in which we have all the values, the co-occurring values. So that is called X. So this is X. This table is X, whose entries Xij tabulate the number of times word J occurs in the context of word I. So how many times word chocolate, let's say, occurs in the context of word I. And then tabulate the number of times word J occurs in the context of word I. Let Xi equal the sum of all the so Xi is going to be the sum of all the for example, so Xi is going to be, for example, for the word I. So for all this, we are just going to calculate it. Yeah, for example, for the if I is equals 1 for the first row, we are just going to like add all the values. So we are going to add all these values, and that is going to be Xi. I don't know why they are doing, because we're just understanding the notation, right? So we're just going to add all that, which is going to be, so it would be the number of times any word appears in the context of word I. So we are just going to add all these probabilities, I think, all the word occurrences for this word I with respect to all the other words, and we'll just add that, and that will be the number of times any word appears in the context of word I. Finally, let Pij equals the probability of J occurring I. So we'll just have a probability called Pij. So Pi, for example, P I like. So I'll just write it. let's say the probability of, so the probability of I, say given the word like, so this is so what it represents is like, um so how many times or how likely is it that I will appear given the word like. So let's say we have a the word like in the sentence, so how probable is it that the sentence contains I in the context of the word like. Right, so that is what this probability is telling. So that the probability of j given I, the probability that word j appear in the um context of word I. We begin, so this is the, I think, a very, so yeah, this is an example of the table. For example, we have specific some very random words. I think ice, steam, solid, gas, water, fashion. So P of k given ice is nothing but, so we are just going to calculate P of k, probability of the word k. So here k is values. So k carries a variable, many words for each column. So P of k given ice. So probability of word k occurring when given ice. So the probability of the word solid given ice is, I think, pretty small. But still, I think it is pretty big in the contextual manner. Like we are going to have a very huge data set, right? So it's actually very high compared to this other things also. So it is very high. It is pretty high, and the probability of the word gas given ice is pretty small compared to the other value, and the probability of the word water given ice is also pretty small. It is pretty small, and the probability of the word fashion, which is completely non-relevant given the word ice, is very pretty large. Right, not very large but pretty large. And the p of the probability, and the same for the word steam. The probability of word k given steam, the probability of word given solid, the probability of word solid given the word steam is pretty high. The probability of word gas given steam is also is pretty low compared to the other value. The probability of water given steam is pretty low, and the probability of word fashion given steam is pretty high. And this thing, probability of the word k given ice by probability of word given k, the probability of k given steam. So we just calculate how likely is a word related to ice, and how just like, for example, if the value is very large, then that means the word is closely associated to the word ice rather than steam, right? So 8.9 solid. So therefore solid is more likely, or solid is more closer to the word ice than steam. So we have this table. Just go to the table if you like to, right? And then similarly for words k related sum, not say, okay, so let's skip that. The above arguments, so it is also better to discriminate between two relevant words. The above argument suggests that the appropriate starting point for word vector learning should be with the ratios of co-occurrence probabilities rather than the probabilities themselves. So we'll be not taking the probabilities, but we'll be taking the ratios of probabilities, which is going to be pik by pjk. Right. Depends on these three words, ij. The most general model takes the form the f of wi, wj, wk, whereas I think the w represents w represents the word vectors for each word. I, j, and k represents each word. So I'll just show that. Yeah, so we are just going to have one word k, and we're going to get that to both I and j. So yeah, probability of ik by probability of jk. So given two words, ice and steam, let's say we're going to calculate the compare this word ice and steam with all the other words in the let's say vocabulary. So in this so yeah, so this is going to be, I think, the main thing that we are doing, the function. Yeah, so in this equation, the right hand side is extracted from the corpus, and f may depend on some as of yet unspecified parameters. The number of possibilities for f is vast, but by enforcing a few desiderata, we can select a unique choice. So first we like f, the information present in the ratio in the word vector space. Since vector space are inherently linear structure, the more natural way. So what we are doing is we can restrict our concept. Okay, so this since vector space are inherently linear, the most natural way to do this is vector differences with the same, we can restrict our consideration to those functions f that depend only on the difference of target. So yeah, so basically we'll just I think subtract the word vectors between wi and wj, and we'll so based on difference, I think, so based on this difference, we're just going to calculate that. And I think there are a bunch of mathematical formulas in which they'll get the transpose, and I think they're just doing a bunch of things. Yeah. So which by equation 3. So we have equation 3 also here. We're just going to get the equation 3 and plug in there. So anyway, so there is, we just get the final formula. So this is the final formula that they have gotten us through. So the log of p of ik, so the probability of the word I given k is equal to the log of xik minus the log of xi. So, and that is equal to this dot product between wi transpose and wk. And I think so if the dot product, so I think dot product represents similarity between two words. So if the dot product is higher, that means two vectors are similar. So I think the dot product is directly proportional to the log of pik, the probability of the word I given k, and which is equal to the log of xik, right? Xik is so we're just going to get the log of xik, and we're going to subtract with that with the log of xi. So basically, I think we can just subtract both of these values and get like a loss function or something. I think that's what we'll do. So and we also add a bias. And I think where is it gone? However, this term is independent of k. So yeah. So this is the final equation. I think wi transpose wk. So the dot product plus some bias, and that is going to be the log of xik. And then I think this is going to be the loss function. Yeah. So again, the same thing. We're just going to take this equation, the left hand side, and going to subtract that with the right hand side. And that will essentially be our loss function. We're just going to try to, just given the similarity, given this co-occurrence, we'll be trying to update these weights such that the difference between x log of xij and this calculation is as small as possible. And we are going to update these weights such that the difference between them and log of xij is as small as possible. Then that will be our loss function. Right. So that is the model, I think. And I think that is glove. So hope you understand what is going on here. So they're just like bunch of mathematical formulas. I think we could just look at the final equation in which we have that we're just going to get the dot product of the weights or the vector representations, and we would make sure that the dot product between these vector representation is equal to the log of xik, such that we're just making sure that our prediction of similarity is equal to the actual similarity. Right, so that is the concept of word glove embedding. So thank you for watching. I'll see you in the next one. Thank you.